In this screencast, we are going to look at how to solve this endothermic CSTR example using Matlab. In this endothermic CSTR, we have our initial feed rate, or our feed rate is F equals 10 kilograms per second. We have our inlet concentration Ca0 being equal to 1 mole per liter. This endothermic CSTR has a jacket which is heated by steam, and that steam heat load has initially a Q dot of equal to 1.2 times 10 to the 6th calories per second. And then at time t equals 10 seconds, this is going to shift to 1.32 times 10 to the 6 calories per second. Now also, other important constants that we're going to need to know is that the reactor has a volume, VR. Its outlet stream, Ca, at time t equals 0, is equal to 0.25 moles per liter. And then, of course, at time t equals 10 seconds, that's going to change because the heat load will change. Now the equations for this CSTR are as follows. So the first equation here, we have our equation for our mole balance, our equation for our energy balance, our equation for the dynamics of how the heat load changes when the specified heat load changes. Pardon me, that's what changes at time t equals 10 seconds. The heat load doesn't change at time t equals 10 seconds. The specified heat load does. So the specified heat load changes at time t equals 10 seconds, and then you have the dynamics of the actual heat load as it propagates through the heat exchanger, which then gets to the steam heated jacket of your endothermic CSTR. There's also a temperature sensor that we have to worry about, which is on the outlet stream. There's a temperature sensor here, and the dynamics of the sensor value are follow this equation. Now also don't forget that for simplification, I've made the dilution rate D equal to the flow rate, the mass flow rate F, divided by the volume of the reactor times the density. I've captured the Arrhenius dependence of the reaction rate constant just through this K of T, which is equal to K0 e to the minus E over RT. And for simplicity's sake, what I'm going to do is I'm going to replace this term with a constant little q, and this term with a constant little h, which are illustrated by these terms here. So using these equations and also some other constants that we're going to define in the problem so that we have the values for all of our parameters in these equations, we're going to move over to Matlab and program these equations into our template file. So now that we're in Matlab, this is our template file for our function, which is called by ODE45. This should say ODE45 here. So the first thing that we're going to do in our Matlab template file is we're going to unpack our vector of state variables. So we're going to say that the concentration of A, which is our first state variable, is equal to x1. The temperature of the reactor T is equal to x2. The heat load is equal to x3. And the temperature sensor is equal to x element 4 of our input vector x. Remember, our input vector x is the vector of state variables in our problem. Now before I go any further, I want to save it, but I don't want to save over my ODE45 template, so I'm going to save as, and I'm going to save this as something called function endo CSTR. Now as soon as I save it as a different file name, Matlab will complain to me that the file name does not match the name of the function as given here, so I will just change that quickly. Okay, so now we want to define our constants for our problem. So first we have our flow rate F is equal to 10, and that's in kilograms per second. We have Ca0 is equal to 1, and that's moles per liter. We also have several other constants in our problem, like the temperature of the feed should be 400 Kelvin, and our heat capacity of our fluid, which is roughly the heat capacity of water. We also have our other constants in our problem, like the base reaction rate constant, our activation energy normalized by R in Kelvin, our reactor volume in liters, our density of water, or density of the fluid in kilograms per liter, our delta H of reaction, and our two time constants, one for the heat load and one for the temperature sensor. Now there's something I want to point out here. This example comes out of the book, but the book has some units that are actually wrong, and so it defines its CP in terms of grams instead of kilograms, and that throws off all of the calculations. And so when you want to run Matlab doesn't know about units, it just knows about numbers, and so you have to be the one responsible to make sure your units match up right. So if you run the numbers that the book has given you, then the book multiplies CP times density, but the CP is in grams down here and the density is in kilograms, and so you don't get the proper canceling of units the way you should. And so in reality, the book is running with a heat capacity of 1/1000th that of water. And in order to make up for that, you have to make CP equal to 1000 to actually run the correct numbers. And in addition to that, those are the constants for our problem, but also we need to program in an if statement, which tells us how the specified heat load is going to change when time t equals 10 seconds. So if t is less than 10 seconds, then the specified heat load will be 1.2 times 10 to the 6 calories per second, and when t is greater than 10, it'll be 1.32 times 10 to the 6 calories per second. Now, one thing that's true about this problem is that there are a lot of different parameters there. The equations are a little bit hairy to work with, and so what we want to do is we want to group together some of these constants for easier writing of the equations. So how should we do that? First, I'm going to define little k as equal to my Arrhenius rate constant. So that's equal to K0 times E to the E over R divided by T. Now note that T has to be in Kelvin because of this Arrhenius relationship. So now whenever Matlab encounters this K, it knows that the K takes on the value of K0 times E to the minus E over R over T. Similarly, we're going to define our dilution rate as D is equal to F over the volume of the reactor times the density. And in addition to that, we've also defined Q as equal to the heat load Q divided by, sorry, I should be more precise, little q is equal to capital Q, which is the heat load, normalized by the volume of the reactor times the density times the heat capacity. Finally, we also have a normalized heat of reaction, little h, which is equal to delta HR over the density and the heat capacity. So those are our constants grouped together for easier writing of the equations. The next thing that we have to do is we have to define our functions. So it's actually fairly simple to type these equations directly into Matlab just from the equations that were given to you on paper. And so these 4 lines of code here represent the 4 equations as they were given in the lecture notes that were on paper. Now note that you have the little h appearing here, which is your normalized delta H of reaction, and the little q, which is your normalized heat load. So just for one moment, let me kind of reveal to you what the equations would look like if you didn't group these constants together for easier writing of the equations. So the first two equations would look like this, which really aren't that much more complicated than the simplified versions of the equations where we grouped all of the constants together. But once you start to get things that, equations that are that long and that difficult to read by eye, then it's a lot harder for you to debug if you make a mistake. Furthermore, one thing that's very obvious is that this grouping of the constants d appears twice, as well as this Arrhenius term, this little k. And so all you have to do is write that term once, and then the simpler term appears twice, the little k and the little d. The reason why that's important is because if you want to have the expanded version of the equations, and you write in here, instead of capital D, you write this grouping, the next time you write it, the more times you write a more complicated equation, or grouping of constants, the more likely you're going to make a typo. And so that's another reason why the simpler form of the equations is better. Okay, so the last step here in this function is to pack up my four differential equations into my vector output, and they have to go in the order that I unpacked my state variables originally. So the state variables were unpacked in this order. First was the concentration of A, the second was the temperature, the third was the heat load, and the fourth was the temperature sensor value. So all I have to do is put into this vector, in the right order, the four variables that are shown here. Copying and pasting them is not just a shortcut, it's also a way to avoid typos. So it's easier to make a typo if you have to type something twice rather than just once. Now there's one more thing that I want to show you, which is sometimes people might suggest that instead of writing out your four equations here and then packing them back up into this vector form, you can actually just write them all in one line right here. So let me show you what I mean. So now this one line of code here is equivalent to what I had before. The problem with it, again, is that since it's all packed into one line, it's a lot more difficult to decipher. So if you're trying to debug your code and Matlab is telling you you have an error on this line, where do you start? Furthermore, it could be even worse if you look at the expanded forms of these equations. And you're trying to pack everything into one line. You can't even make sense of what the equations are anymore. And in fact, they also run off the page. So now imagine that you try to write your equations this way. How are you going to debug that? I can't make sense of it. There's actually even one more step that some people would like to write their code this way that makes it even more difficult to understand. So remember that CA was our first state variable. So it was the first element in X. So everywhere that you see the variable CA, what if instead you just wrote X of 1? That is an acceptable way to write this code. Everywhere where you see the temperature T, you write X of 2. This code will still run. It'll still work because MATLAB understands it just this way. Capital Q is replaced by capital X of 3. But you can see how difficult it is to even understand what this code is doing. But sometimes when you read examples of how to program in MATLAB, this might be the way that people suggest you write your code. And I strongly advise against doing all of this. All of the steps that I've suggested here, whether it's grouping your constants for easier writing of your equations, unpacking your state variables, or writing your code so that you have everything on separate lines for your four differential equations, and then repacking them back into your output variable, into your vector output, which is your derivative of your state functions, state variables. That is a much cleaner and easier code to interpret. And so I strongly advise that you would do it that way. So now that we have our function saved, let's switch over to the script file, which we'll call ODE45, using that function. So the first thing I'm going to do is I'm going to save this as a new file. I'm going to call it script endo.CSTR. And just as is my habit, this first comment here on the first line of the script, I'm going to have that match the name of the file. And in addition, I've also changed this third line here, which is a comment that describes what the script is for. Okay, so the first thing that we want to do is we want to define our constants for our problem. Now, just like in the other example in class, we actually will not need the constants to be defined in this script. So let's go ahead and leave that part out. Because of that, we also don't have any grouping of constants for the writing of the equations. So the first thing that we'll have to do is we'll have to solve our equations. And to solve our equations, the first step is to define our function handle, which was ftn function endo.CSTR. That is the function that we want ODE45 to go to. Our t-span is actually correct. We want it to go from 0 to 100, or let's go ahead and start that way. We might want to change it later. Our vector of initial conditions, this is not right, and we know that because we have 4 state variables, so at the very least, you need 4 initial conditions. If we look back at the lecture notes, these are the initial conditions. Initially you have your concentration coming out of the reactor at 0.25. You have 350 degrees Kelvin. You have our heat load is 1.2 times 10 to the 6, and also 350 Kelvin is the temperature sensor value. So now that I've defined all of those, the next line is actually just correct. We can go ahead and run ODE45 just like that. But before we do that, that's not going to help us any because it will solve the equations, but we won't know what the solution looks like. So the next thing that we want to do is we want to unpack our output state variable array into the 4 state variables. So the first column of the output array, capital X, will correspond to our concentration variable, the second column to our temperature variable, the third one to our heat load variable, and the fourth one to our temperature sensor. Finally, we want to plot the output. So this code down here in the template first opens up a figure window and then plots as a function of time the variables x1 and x2, but of course we're going to replace that with the variables CA. We're going to open up a new figure window and replace the second one with T. And I'm going to plot in the same plot, I'm going to plot both T and the temperature sensor value. We can also open up a final figure window and plot versus time, we can plot our heat load. Okay, so when I run this script, this should work. And when I run the script, I get 3 figures appearing. The first one is for my concentration. The second one is for my temperature and temperature sensor. And the third one is for my heat load. As you can see, the heat load acts the way you would expect it to. It starts at 1.2, and at time t equals 10 seconds, it starts to rise, and then levels off at its new steady state of 1.32, which is the final Q spec. So that's fine. This graph doesn't look very good. There's a lot of jigglies in it, and I don't think they're real. So I think these jigglies are the result of some numerical difficulty that ODE45 is encountering when it's trying to solve these equations. This looks fine. Actually, if you zoom in a little bit more, you can see that there are also jigglies in this graph, both in the beginning and the end of it. So it's possible that ODE45 is just not a robust enough method that we can use to solve these equations. So let's go ahead and run this script again, but let's change it to ODE15S, which might do a better job. Before we do that, I'm going to go ahead and change this code here to make my figures more beautiful. So what I've done here is I've made the line widths bigger, I've changed the font size on the graph, and I put X and Y labels, and I've done that for all of them. Oh, in addition to that, on the second one, I've made a legend, which will tell me which curve is my outlet temperature and which one is my sensor value. So let's go back up and change ODE45 to ODE15S. That's the only change we're going to have to make. And now we will run this script by clicking the Run button. And 3 figures should pop up, just like before. So here is our heat load. That wasn't that much different. It worked before. It works now. The X label is a little bit outside the video there, so that you can see it. Here is my temperature graph, which works better than it did before. There's no more jigglies. And here is my concentration graph.